So I'm Simon Miles. I work for AeroAgility, which is a small company, so around 25 people, um, that does simulations for forecasting and planning within aerospace. So sort of managing the fleets of aircraft and their components and that kind of thing. I'll give you a little more detail in a moment. So the context, as Stefan said at the start of this session, my background is not in model-driven engineering. In fact, I was an academic in prior to 2002, 22. So for 20 years, I was in the AI and specifically multi-agent systems area. So that's part of symbolic AI. I was a researcher and academic. And also, importantly for this talk, AeroAgility itself is not based in model-driven engineering. I don't, most of my colleagues, I don't think would know about model-driven engineering, but actually, sort of as we've explored the direction that we've taken, the business direction we've taken, driven by the business requirements of our particular customers, then we've found that the ideas of domain-specific modeling languages fits very well into actually what we've done, fits our requirements well, and is a useful way of thinking about how to solve the problems that we still have open, right? So the new requirements that we are getting from customers and the development of the sort of the AI offering of the company. And it becomes important as well, thinking about the nature of this session, that we've sort of moved from producing a piece of software which is used by, let's say, a single planning team within an organization as an individual tool, to something which is touched by multiple parts of an enterprise, of an organization, which are themselves reflected in the simulations that we run. And you've got the data going in order to keep that simulation up to date and matching the reality, and you've got outputs automatically affecting what's going on in the real world. And so what we produce is effectively turned into a digital twin because that's what our customers need. And so what I wanted to show in this talk is how the sort of the ideas from domain-specific modeling are influencing our thinking as we're going forward. So just one slide sort of on us as a company to give a bit of context. So our customers tend to be either airlines or OEMs, so engine manufacturers, equipment manufacturers. So we have like EasyJet and Jetstar and Vueling and Scandinavian Airlines and so forth, who use AeroAgility, so as a piece of software, in order to plan out how they're going to maintain their aircraft fleet so that they can keep their aircraft flying, they can get people on holiday or whatever it may be. And there's many questions within that, right? So how do you best make use of limited maintenance resources? Where and when do you get components from? What skilled people might you need? What contracts do you enter into with component manufacturers so that you own or lease the right pieces at the right time, and so on. And then you've got the manufacturer side. So Rolls-Royce and Lockheed Martin have been long-term customers, again in this sort of aerospace area, where they themselves have customers and they're trying to keep fleets of aircraft available for whatever the needs may be. So sometimes that's civil, but sometimes that's on the defense side, right? So making sure that enough aircraft are available to perform missions or mission rehearsals or something. Our software is not really specific to aerospace. That's more about our expertise, our business expertise, that we know the domain and we can talk to people. We understand the problems that aerospace faces. The software itself is more about asset management in general and the things around it, so supply chains and training and various other aspects, which I'll sort of illustrate as we go along. So the way that I structured this talk and how I thought it's best to explain the messages I want to get across was in terms of sort of the requirements that have driven us to design our software in the way we have, and why the ideas from domain-specific modeling languages fits nicely to that, even if that's not how we originally thought, and we've never, touched EMF or anything like this. So just from the top, first of all, we've got our core business, right? So we've got users who are largely non-technical, by which I mean they're not programmers, and in fact, we'll dig into that a bit in a moment. In the aerospace domain, they want to flexibly generate some forecasts, and those to accurately reflect the constraints on their specific enterprise, so that they know where there might be problems that they need to face in the future when they're maintaining or upgrading their equipment. They want to both ask what's realistically going to happen under some possible circumstances or business strategies or whatever it may be, and also what the best thing is that they could do given those constraints. And those are two slightly different questions. And again, I'll come to why the sort of domain-specific modeling languages view is a natural fit to that different forms of execution. We are a small company, right? So we're only 25 people. What they want to do includes a lot of rich information, a lot of rich domain constraints and logic that our customers want to include in the software. There's only so much that we can maintain. There's a lot of commonality between our different customers, but then there are points of great diversity as well. And so there is a software management need. As I mentioned, the results and the models that we produce are used in diverse parts of an organization. So our customer organizations, so not just data scientists or planners or mechanical engineers, but up to financial people, people looking at it from a strategic business point of view, and so different sort of parts of an organization. And we need that sort of ability for all of them to access it. And then there's sort of a very important point, which is our users will be producing these forecasts. They need to be able to judge whether they can rely on them or not, right? So we try to make things reliable, but that's dependent on the model logic and what's put into it, right? The data that's input into it. But they're making large business decisions on the basis of them. So I want to talk about how domain-specific languages, just the concept sort of helps us when we're thinking about our needs going forward. As an introduction, because I don't know the knowledge of the audience in terms of agent-based modeling, which is the form of computer simulation we use. So our simulation is trying to mirror the real world. Okay, so it's a digital twin at a sort of enterprise level, so this high level view of an organization. And by simulating, we're in particular allowing people to look at long-term effects of different strategies they might enact, or different circumstances that might occur. So obviously the pandemic had a particular effect on airlines, and they needed to understand how to best use their now more limited resources in order to maintain their fleet through the pandemic. And with agent-based modeling in particular, we're talking about a bottom-up modeling technique. So that means that we simulate as autonomous individual components each element of an organization, and these have their own logic and they interact with each other. Okay, and so agent-based modeling comes from agent-based systems, where you're sort of taking a folk psychological perspective of saying, okay, well, this is what this part of the organization knows and wants to do, and the strategies by which they typically do it, and then look at how they interact with each other to see the overall emergent effect. These simulations are often probabilistic, right? You're not trying to pretend you know exactly how decisions will be made, for example, or whether a bird will get sucked into an aircraft engine and require maintenance. You're saying there is some probability by which those things might happen. So then stepping back to the first requirement, okay, so we've got the need for our users, who are not typically technical people, to be able to flexibly create forecasts and plans using our software. Within our space of competitors, so people providing different forms of simulation software, there's sort of a number of different approaches, and this is a very crude description, but it sort of tried to get across the general idea. We've sort of got on the left-hand side, there are organizations which produce general purpose simulation engines, or just start from a high-level general programming language. And then typically a consultant will create a highly tailored model for a customer on top of that. And then they give it to the customer and the customer uses it, right? And then there is potentially some interaction after that, but often the customer is mostly left to do what they want, and there's sort of these long contracts in order to make any changes. So with that kind of highly tailored model, obviously, it's done in a specific instance in time, and the customer requirements will expand over time as they realize there's other things they want to simulate. So you get sort of high usability because the simulation they've got exactly matches their domain, and fine granularity up to the point that they'd originally specified it, but typically low flexibility because it's quite hard to go beyond that initial model scope. On the other side, on the right-hand side of my slides, there are simulation platforms which provide you with concepts which are generic, say process steps, for example, for if you imagine flowcharts, for example, from which you could use as a customer, you could use this off the shelf to construct a description of the processes that occur within your enterprise to be able to then simulate them. But they are quite generic, right? So you have to use your imagination in order to match them to your particular domain description, and it's very hard then to get into domain specific logic, right? So if you say, okay, well, my aircraft maintenance works like this, I select which particular aircraft I'm going to start to try to fix on the basis of some particular criteria, then you haven't got support for that domain specific information within the tool because it's not because it is not intended to be domain specific. Okay, so you've sort of got high flexibility, at least up to the limit that this generic concept scope gives you, but you then have fairly low usability because you've got the hurdles of getting over it, and you've got potentially quite low granularity because you can't really drill down to the individual ways that your specific enterprise works. And then we try to sit in the middle, and this is really just driven by the needs of our customers over time. So starting with organizations like Lockheed Martin, which came to us to help to plan the modifications and upgrades to the aircraft fleet they were maintaining, where we provide a sort of customizable domain engine where there is a lot of domain specific knowledge put into it, and effectively a domain specific language, which is then tailored for a particular customer. And then there is we just have this relationship over time of saying, okay, well, we know that the domain is not exactly going to match how you do things, but it will largely match it, and now we can tailor it as we maintain this relationship. So we get a higher flexibility than if you just use a generic purpose simulation engine, because we are limited to the domain scope but not to the initial model scope, and we have better usability than if we use just a generic process type of simulation, because it has some domain specificity, and this can be updated over time as well, right? So it gets better and better as they use it, which is why we sort of have long-term customers. And then I should also mention that there is also a lot of legacy domain-specific simulators that float about and are used within many organizations, which can be fairly simple and were just created at some point in time and then reused. And sometimes they are interesting, in their sort of discrete event simulators or something, or sometimes they are very basic in that they're really just front ends to spreadsheets. So then, if we take domain-specific modeling languages as an idea, then this is my understanding. Again, I'm not a model-driven engineering person, but a domain-specific modeling language is a custom modeling language using the vocabulary and notations found in target user domain. We think in terms of concrete syntax and abstract syntax and the semantics of the language. And the benefit of it being domain-specific is greater productivity, better communications, and execution abstraction. I'm sure there are more, but these are the key ones for us. And so what I'm going to do here is just to sort of show how the concrete syntax, the abstract syntax, the semantics sort of map onto what our software looks like as a tool. And then as we go through the other requirements, these benefits will become clear as well, I hope. So this is a screenshot from AeroAgility. I'm happy to give a demo to anybody who wants to know more later. So here, what's happening is that the user is constructing a specific model to simulate some particular hypothetical scenario. They have a set of tabs for allowing them to see different agents and objects and types, and then within those they've got these particular agents and objects, and then they will add a set of agents. So in this case, we've got aircrafts. We may have multiple aircraft groupings, aircraft manufacturing, maintenance facilities, and if this was for submarines rather than aircraft, then obviously the naming would change. But actually, the configuration would remain largely the same because many of the parameters will still remain the same, given this is about asset management. Okay. But this is then their language, right? It is a visual language, and this is the way that they describe their model, and then that can then be simulated. And just stepping back, then the fact that we're using an agent-based simulation means that we already have some idea of the structure of a model even before we get to the domain specific. So with an agent-based model, what we're saying is there are agents which are really areas of responsibility. So parts of an organization that are making decisions, whether that's a facility or the team looking after an aircraft, or sort of a procurement side of things, right, or a logistics provider. Those are different areas of responsibility which will do their own individual thing. So that's sort of our high level structure. And within that, there's the sort of agent-based ideas which break down the parameterization of those agents. So some of the way you configure them is to do with their logic, some to do with their motivation, right, what they're aiming for within a simulation, how they interact, what state they can have, and so on, right? But what the customer sees is all of this domain-specific information. And so, when they look inside an individual aircraft, for example, or in this case, an aircraft maintenance facility, they will see a set of parameters which influence the simulation, influence the simulation logic so that they interact in a particular way, and you see a particular outcome, which might be, the costs changing over time, the aircraft that are still flying, changing over time, where they're in maintenance, what maintenance is being performed, and so on. So this model that a customer constructs will then, when you tell it to run a simulation, be translated into an object model underneath, and then that goes into the simulation platform. And as we'll look at in a moment, that can mean different things, right? So there can be different forms of execution over that model. Because we are here trying to cover a lot of different customers with slightly different requirements, there is a lot of flexibility in the model, and that means you can have invalid combined configurations of things. Okay, so some elements just won't quite make sense together, or they won't interact. And so there is a need for validation. Okay, so there is an idea of a semantically correct model, which the expressivity of the language goes beyond, and there needs to be a point in time in which you say, well, this is valid and this is not. So here we've sort of see a screen where the user is selecting between landing gear that has some corrosion issue as opposed to landing gear that doesn't have some corrosion issue. The corrosion issue in that case meaning that you have to perform maintenance more frequently, which will have effects on your supply chain, how constrained your maintenance facilities are because they're full of aircraft requiring their landing gear to be checked or possibly replaced, and so on. Okay. So hopefully this sort of gives you, just in terms of the first requirement, the idea of why we are thinking of this as a domain specific language we're providing within our simulation tool. If we look at how then we go one step beyond creating the model and say, well, what do you do with that model? Then actually the idea within simulation is that a simulation model can be used for many different things, right? So it can be used for prediction or forecast. It can be used for as a locus for discussion. You can use it for generating hypotheses and so on. And specifically for us, there are two important execution contexts, right? There are two particular uses of the model which is created. One is scheduling and the other is forecasting. So scheduling is the customer saying, what is the best plan that I could follow given the constraints that I've got and given some assumptions, right, about how things are going to turn out. And then forecasting is what will realistically occur given a plan or strategy. So if I'm looking over 10 years, how are things going to pan out? And these are actually two different problems. Sorry, these are two different problems to solve at the execution level, because scheduling is an optimization problem, right? You're trying to search for the optimal plan. For example, here we see on the slide sort of a Gantt chart type view, which is produced where we can see that where the maintenance is occurring on different aircraft, which might be about, in this case, replacement of components. Whereas forecasting is a straightforwardly simulation perspective, right? So it is where you are just playing out over time to see what will occur. And so they require different kinds of execution, right? So different forms of execution, different algorithms. But they are based on the same domain model. So one of the values that we get from having this separation of the model from the execution context is that we've got that portability. Okay, so we can take the domain model and we can execute it in different ways. So moving on to sort of where we don't have the answers, but is interesting to think about the future directions, then one thing we've got across our customers is a lot of commonality, but then also a lot of diversity. So within our aircraft customers, okay, so they typically want to just make sure that none of their aircraft are grounded so that they can fly people around, and they don't want to perform more maintenance than is necessary. But then they start to care about the supply chain, right? So they need components in order to make sure that their aircraft are airworthy. And they, if they're thinking about their supply chain, then they need to think about storage. They need to think about production. They need to think about replenishment rates and so on. And then we get customers that say, well, actually, I'm not really interested so much on the maintenance side of things. We're interested primarily about the supply chain and simulating that and understanding strategies around that. And then we've been talking with, for example, supermarkets, right? And the models that they've got around supply chain, the things they want to model, are not radically different, right? They use many of the same concepts. And the difficulty we have here is that it's unclear where our domain scope ends, what the edges are. So not everything makes sense in combination. So if we're talking about the expiry date of some yogurt that makes sense in the supermarket case, but the expiry date of some landing gear in the aircraft case doesn't quite make so much sense. And we have this issue that, of course, we can't maintain too many different software bases, and if we've got this overlap between different customer domains, then we need to understand, well, when does it make sense to say, well, this is no longer the same domain, this is a separate one. And I'm sure as a model-driven engineering community, you would have a lot more answers to this than I would. Sort of in the same scope, then, our modeling language for users is very declarative, right? So that's the primary starting point, is you're filling in parameters which then affect the logic, but you are simply stating them. But something, and in general, that's great, right? That really helps the user, because they are not thinking of things in a programming type of way. They're saying, okay, I want to just describe my domain, then let the simulation run and execute the particular code which we've built, and see how things pan out. But it is a disadvantage when actually what you want to simulate are processes. So, if we say, well, you can have a fault on a component that has that can lead to secondary damage on other components within the aircraft, and so you can have these knock-on chains of effects. How might you best describe that in a declarative way? It may be that actually it's best not described in a declarative way, and we start to have to maybe think of a more textual language, exposing a more textual language to the user. Moving on to the sort of digital twin side, then, as I said, we sort of, the software starts to be used by multiple departments within an organization, and we have the
as well.
Oh, sorry, Stephen. Is that?
So just giving you a two-minute warning there as well.
Oh, 2 minutes, right. Thank you. So I will make sure I get through these. So we also have input of data into the system and output of data from the system, because we need to keep our digital representation up to date with whatever the fleet composition currently is, right? So our particular aircraft and components, what their state of maintenance is, and then the output is that it goes into the actual actions of the company, and then those have to be fed back into the software so that it knows what maintenance is already occurring. And this requires a language itself, is the main point I want to make. So I won't go into all the details because I'm running short of time. But we need a language for describing what is going into the system, whether that is in our sort of traditional way through CSV files or web service interfaces, or if it is through predictive maintenance systems, so doing supervised learning to work out when maintenance may be due, or even large language model input into simulations, such as talked about by Lola yesterday. The final thing I wanted to say about was reliability. So the organizations need to know that their forecasts are reliable, or to be able to judge whether they are or not. There are a set of ways that agent-based models are typically validated, but they have a lot of flaws when it comes to forecasts. And really what we want to say when we want to judge whether a forecast is correct is to say that we can convincingly explain how you got from the starting point description of your domain through the reasoning, the model, to that final output, and for an expert, somebody working for the customer organization, to say, yes, that makes sense. And that means you need to have a language. You need to have a language for describing each step that's occurred in a way that the expert can use, and that they can then feed back into the next iteration of their simulation model. So I realise, sorry, that I'm not being very good at time here, and I will stop there. I will thank you very much for your attention. And as I said, I am happy to show demos to people if they're interested in knowing more about air agility.
Thank you very much. Let's thank